Here are solutions to homework set number 10 for ECE 463 Modern Control. In this homework set, we're going to try to control a cart and pendulum in a ball and beam system using a servo compensator and LQR methods. So kind of starting out, this is what I want to do. I want to let's start out. Take a cart and pendulum system and have this go over to a set point and balance with no air. So that's kind of where I want to get to. How do I do that? Well, the first step is to take the dynamics of the system. This is the dynamics for this semester. Add a servo compensator. What that does is that forces the DC gain to 1. Now I want to find the gains using LQR methods, because that's the current method that we're covering. And find the gains, feedback gains Kx and Kz, such that I have no air per step input, 2% settling time of 8 seconds, and less than 10% overshoot for step response. Now the no air per step input is guaranteed. That's what the servo compensator does for you. The other parts I need to find the feedback gains that do it. So one approach is to use LQR methods. I could use pole placement. I could use LQR methods, just a way to find the gain. So here kind of the idea. I've got my system, ABC, form the augmented system, plant plus servo compensator. To find the feedback gains, I'm going to use LQR methods, and here's my weighting matrix. Here's Q, and there's R. R is 1, and Q weights the servo state. The desired response is shown in red. That is somewhere. There it is. I want to have 0.5 over s squared plus s plus 0.5. That meets the requirements. To do that, let's go back to MATLAB. That's the red line, my target. The blue line is the actual system. I'm a little bit slow, so you crank up the gain. Increase Q, that gives me a quicker system. Probably pretty close, maybe a little bit too much overshoot. So let's adjust the gains. And these are just knobs to play with. If I play with X, it's actually not too bad. This is Z, this is the input to Z, meaning the output X. So this looks like friction, that looks like a spring. Increase the friction, that got rid of the overshoot. Maybe a little bit too much. Let's try 7. Okay. Once I'm happy with that, I've got my feedback gains. And I can see those in MATLAB. Here's my feedback gain matrix. I call it K5. The first 4 terms are the feedback gain times Kx. The last one is times the servo compensator, the integrator, Kz. Now, once I've found my gains, I can then say, here's the response, step response in the linear system. Try it on the actual cart. So I'm going to pull off the K5 that I calculated. First 4 gains are times Kx. Last one is times the servo, Kz. I'm going to form the control law as minus Kz times Z minus Kx times X and the states. Given the input and the states, find the dynamics, the derivative dx. That comes from the cart dynamics. And the integrator is just the integral between position and the set point. And the beam dynamics come from here. That goes back to week number 4 in 463. So anyway, I can now try it on the nonlinear system. So this is what the step response should look like based upon the linear system. Let's try it. I'll start out at -1, tell it to go to +1, let it settle out, then go from +1 back to -1. So there's my step response. The nonlinear system will be a little bit different than the linear one because I've got all the sines and cosines, Coriolis forces, terms like that the linear system ignores. But it's actually pretty close. Going from 1 to here, I've got about 10% overshoot, less than 10% overshoot, good step response. So that is problem 1 through 3, using a servo with LQR methods to control a cart and pendulum system. Next problem. So anyway, on the solutions, there's linear response. there's the nonlinear response and corresponding MATLAB code. Repeat with a ball and beam system. So a ball and beam system looks like the following. I first have to calculate the feedback gains. We'll do that in a sec. Maybe not. I've got a beam. I apply torque at the base. I want to bring the ball over here to some target. Find the feedback gains that get you there, and I want to have guaranteed no error per step input. That means add a servo compensator. So how do I do that? This is actually the same as the last problem. What I'll do is first form the plant plus the servo compensator. That's my augmented system. Find the feedback gains using LQR methods for the augmented system. So one way to do that is in MATLAB. I'll take the plant. Here's the plant dynamics. My desired response, that corresponds to a pull of 0.5 plus or minus j 0.5-ish. 4% overshoot in the step response, 8 second settling time. Come up with the feedback gains to do that, but do that using LQR methods. So what I'll do is I'll first wait the last state, that's the integrator, the servo compensator, check the step response. The red line is what I want. The blue line is the step response to the actual system. So that's too slow, meaning crank up the gain. Still a bit slow, crank up the gain. Yeah, not bad. A little bit oscillatory. To get rid of the oscillations, if this is what it thinks the output is, the input would be y, or the output of the system, which is position x. I can try playing with that gain, see what that does, and it sort of helps. These are really just knobs to play with. I can sit there and see what happens if I wait angle. And not a whole lot better. Let's wait velocity, third state. That looks good. Let's wait angular velocity. I think I like this one best. So just by trial and error, it seems to work best if I wait velocity and servo. It's a little bit too slow, so maybe back up in the gains a little bit. Let's make that 50. Make this a little bit faster, say 200. So I'm really just kind of playing with the gains until I get something that looks good. And it's kind of subjective. Whatever you think looks good is close enough. Not bad. So if I'm happy with these gains, I now have my feedback gains found using LQR methods. So these are optimal gains for a completely arbitrary cost function. So I don't like using the word optimal, but that's what it's called. The first 4 gains are the feedback times the states. The last gain is times the servo compensator. So using these gains, I can now try it on the nonlinear system. So this is the nonlinear dynamics. Mass is 2, beam inertia is 0.5 kilogram meter squared. Important to get those right. I'm going to use the gains that I just calculated, find the control law, use those for the beam, integrate, move forward in time, repeat, and here's what she looks like. We go from 0 to +1. Beam rolls to the right, it catches it, and slows down. And now if I want to go back to the origin, I can do the same thing. I guess I didn't do the same thing. So there's your step response. So really, LQR methods are not a whole lot different than pole placement. When I formed the augmented system, or found the feedback gains, I did place the pole somewhere. And in this case, I put the poles at this spot. If I use pole placement to put the poles in the same spot, I'd get the same gains. What LQR does is it just gives you a couple knobs to play with, and it figures out where all the poles go based upon your cost function. So with pole placement, I can place the dominant poles pretty easily. That dictates the response. The other poles, I don't really know where to put them. With LQR, it all kind of drops out. Here's my dominant pole. That kind of dictates the response. These are the other poles. For my cost function, that's where they belong. So that is homework set number 10 for ECE 463, Modern Control.